Now, here is the end user that is trying to access trading.acme.com. The DNS resolves trading.acme.com to the IP address of the IaaS load balancer. The IaaS load balancer then forwards the request to one of the Go routers. As per the configuration discussed earlier, the Go router terminates the TLS from the client side, and it uses its own certificate that are managed by platform to do so. Go router then uses its local map for trading.acme.com. It picks up one of the IP port combinations based on the application load balancing. Let us suppose it picks up 10.0.4.9, port number 61006. Go router opens a new connection to this IP and port and sends the request there. If the end user has sent a client certificate, then the Go router puts that certificate into the XFCC header of that request that it sends to the application instance. This way, if the application wants to retrieve or the application developer wants to use the client certificate, it can do so by retrieving that certificate from this header. This is useful if application wants to verify the authenticity of the end client. This is good for service to service or app to app communication if additional authentication is required. Now, when the request reaches the Ego cell and port, in this particular case 10.0.4.9, port number 61006, when it reaches there, denatting takes place here. The destination IP is changed to that of the container IP. The traffic is then sent to the application container via the VTAP. This denatting, the VTAP, routing table, etc. are all kernel features. We don't have to go into the details of that. The important point to know is that the CNI plugin has done the required setup, and the actual execution of that is a function of a kernel. The containers envoy proxy receives the request, and it terminates the TLS from the Go router. Envoy then sends this request to the application container application process within the same container on localhost. Now, the routing table here also plays an important role as a firewall. It prevents any east-west traffic. If you need east-west traffic, that is from application A calling application B directly on the overlay network, then the operator has to enable that such a communication using application to application basis using network policies. This is a topic of a different discussion based on container to container networking. The critical point from security point of view is that even if someone pushes a malicious container, it still cannot establish a direct connection with the other application containers. This ensures complete routing security for every application container. Well, this is a lot to digest. So let us summarize the layers of security here. First and foremost, we have to ensure that the infrastructure network security is there. From the point of view of application platform, PCF ensures security of the application routes. And none of it requires any tickets or any manual process or any custom code. Now, whether it is certificates at the Go router for client TLS termination, whether it is application container creation itself, the Envoy sidecar proxy with the application identity certificate, or the rotation of the certificates, or the firewall to prevent east-west traffic. All of it is done by platform. Now let us discuss about Mutual TLS. Let us see how platform's Mutual TLS capability further enhances Acme's security posture. Let us consider a corner case threat vector. Attacker breaches infrastructure security and manages to find the cell IP and ports for application route. If such a thing happens, then the attacker can potentially send requests to the application via this cell IP and port combinations. Of course, there has to be internal application authentication and authorization that will prevent illegitimate access. But let us suppose the attacker has managed to retrieve even the application credentials. Well, this is where the platform provided Mutual TLS really helps. In case of Mutual TLS, the server authenticates the client during the TLS handshake, and this is done using client certificate. In this case, the application instance validates that the caller is actually the go router. The benefits of this additional layer of security is clear. Even if there is a breach in IaaS security, even if somehow attacker has retrieved application credentials, the malicious code still will not be able to access the application instances. Mutual TLS provides that layer of defense in depth. Now let us see how it actually works. Now, when the mutual TLS is enabled, the application instance envoy proxy gets the certificate authority of the Go router certificate and the subject name in the certificate of the Go router. Now, when the Go router creates connection with the application container, it sends its own certificate during the TLS handshake. Envoy, which is in the application container, authenticates that the caller is actually the Go router by validating the certificate. The certificate is validated against the certificate authority and the subject name that already is placed along with the envoy sidecar proxy. So any malicious code sending request will fail because it won't have the certificate of the Go router. As seen earlier, the platform manages the certificates of the Go routers. With so much security natively built into the platform, Acme CIO decides to pick Pivotal Cloud Foundry instead of building his own platform. And he has business outcomes to brag about. Well, Acme has rapidly been scaling their application dev team. They're pushing new innovative applications on the platform, and yet they have only 3 platform operators to handle like more than 140 new applications. On the other hand, Acme's competitor is busy building its own platform. Well, here I conclude my session on application routing security provided by PCF. Thank you.